After decades, humanity is returning to the Moon, but this time the goal is sustained presence. This long-term lunar mission requires a persistent infrastructure, not just temporary landers. To support the Artemis program, NASA and its partners created a crucial piece of hardware. This is the Lunar Gateway, a space station designed to orbit the Moon indefinitely. Gateway's mission is to act as a crew, science, and logistics staging point for all lunar missions. It will be an outpost in cislunar space, a region between the Earth and the Moon. However, this station is not in a low lunar orbit like the Apollo missions used decades ago. Low lunar orbit is efficient for landing, but it requires constant high thrust to maintain altitude. By contrast, Gateway orbits far away from the Moon, often more than 40,000 kilometers. The chosen orbit is strange and distant, but it is actually highly efficient for long-term use. This positioning means Gateway requires very little fuel to maintain its long, sweeping path. This fuel saving is critical for long-term sustainability and future missions toward Mars. Next, let us explore the physics behind this unique orbital choice and its powerful efficiency. This stable, distant position is the key to Gateway's role as the logistics hub. We will see how this station will become the permanent gateway to the entire lunar surface. Now, zooming out, let us see the complex gravitational interaction of the Earth and the Moon. This combined system is a continuous tug-of-war, with gravity and momentum constantly shifting. The physics of this orbital dance are not simple, unlike a single satellite around a single planet. Instead, we must use a calculation called the restricted three-body problem, or T-text. T-text. This calculation determines the gravitational stability points between Earth, Moon, and the spacecraft. The three-dimensional analysis reveals 5 specific spots where the forces precisely cancel out. These 5 key locations are called the libration points, labeled L1 through L5. On the diagram, hard text L1 is between the Earth and the Moon, while bulk text L2 is just behind the Moon. The mon text L3 point is hidden behind the Earth, always opposite the Moon in its path.
H-text keyed 4 and H-text 5 are located along the Moon's orbit, forming the stable Trojan points.
These are unknown text L-talon points, are pseudo-stable gravitational balance spots, perfect for staging a space station. The Gateway station is planned to orbit around the non-text L2 point behind the Moon. Orbiting this point provides near-continuous communication with Earth and excellent views of the Moon. The path around text L-talon 2 is not a simple circle, but a complex three-dimensional curve. This unique path is a halo orbit, named for its shape circling the gravity well. The Gateway utilizes a very specific type of halo orbit called Near-Rectilinear. The Near-Rectilinear Halo Orbit, or text NRHO, is extremely long and highly elliptical in shape. Its unique geometry allows it to leverage the Sun's gravity for long-term stability and efficiency. Now, from above, let us examine the crucial details of the in-text NRHO path around the Moon. The one-text NRHO can be thought of as a very close pass, then a very long drift back. The path brings Gateway to a perilune, or closest point, just 3,000 kilometers above the pole. By contrast, the apolune, or farthest point, is about 70,000 kilometers from the Moon. This extreme range creates the nearly straight lines from which the orbit gets its name. This path is highly efficient because it is synchronized with the Earth-Moon system resonance. The orbital period of text NRHO is about 6 days, or half a lunar orbit. On the diagram, the net-text NRHO is designed to minimize the net-text delta on text mun required for station keeping. Text delta in text varstallasta is the measure of the fuel needed to change velocity or maintain an orbit. A traditional low lunar orbit requires over 500 meters per second of the text delta in text vidust annually. That high still text a delta untext voltage requirement means a large amount of fuel must be constantly expended. The one text NRHO stability, however, dramatically cuts that fuel cost by 98%. In fact, the in-text NRHO needs only about 10 meters per second of on-text delta Hal on-text vartlust per year. That 10 meters per second is the same amount of fuel needed for a brief hover in a low orbit. This low fuel requirement ensures that Gateway can operate for many years with minimal resupply. Another massive benefit is the orbital coverage this efficient path provides for Artemis missions. The non-text NRHO swing path passes directly over both the lunar South Pole and the North Pole. This means a lander from Gateway can access either pole with minimal plane change maneuvers. The low-fuel text NRHO therefore eliminates the need to move the whole station for polar access. Contrast this with the Low Lunar Orbit, which can only easily access a narrow band of the Moon. The unique context NRHO is key to unlocking the entire lunar surface for human exploration. This position also provides a stable link to Earth, enabling continuous command and control. The NRHO's stability and low cost are why Gateway is essential to the future of deep space travel. The first module, Text PP, provides power and propulsion for the station. Text PPE Taurus will use solar electric propulsion, a highly efficient low-thrust technology. The second module, Text Halo, provides the crew, quarters, and docking ports. Context. Halo contains the critical systems for life support and communication with Earth. Together, Text, PPE, Tuaha, and NRHO, Halo form the initial core of the Lunar Gateway station. The station will serve as a science laboratory, conducting experiments in the cislunar environment. Crucially, it will be the docking port for Orion, which carries the crew from Earth. The crew will transfer to a human landing system for the final leg to the Moon's surface. After surface exploration, the crew returns to Gateway before starting their journey back to Earth. Gateway is the ultimate logistics hub, providing propellant, spares, and a safe harbor. This continuous presence also reduces risk by offering an emergency safe haven for astronauts. This is why the text NRHO is so important, providing efficient access and safety simultaneously. The station is planned to be permanent, with modules arriving over the coming years. Future modules will expand the lab space, add more crew capacity, and increase storage. The construction process will mimic the International Space Station, assembling in orbit piece by piece. The lessons learned from building and maintaining Gateway are invaluable for future missions. By contrast, past missions were fleeting visits with limited time on the lunar surface. Gateway shifts the focus from simple flags and footprints to long-term human persistence. Now, zooming out, consider how the Gateway fits into the grander plan of space exploration. The long-term goal for Text, NASA, Dons and its partners is to send humans to Mars. Mars missions require large, complex spacecraft that cannot easily launch fully assembled from Earth. The fuel and logistics needed for a Mars trip must be staged far away from Earth's gravity well. Gateway, in the highly efficient Text NRHO orbit, is the ideal testbed for this staging. It is the first critical step toward building deep space infrastructure for trips beyond the Moon. The Text, NRHO, and the Gateway are not just about the Moon, but about the future of deep space travel. This is why this complex, fuel-efficient orbit is the ultimate payoff for Artemis. The station is a testament to international cooperation involving 15 nations. This permanent human outpost will provide unprecedented research opportunities. In recap, the Text NRHO is a pseudo-stable path at the Text L2 point, saving 98% of fuel. Gateway leverages this orbit to serve as a logistics and staging hub for all lunar missions. The station enables access to both lunar poles and provides a vital safe haven for astronauts. Next, learn more about the Artemis program and subscribe for more space explanations. Now let us review the Text L-5 point again, which shares the Moon's orbit. These Text L-4 and Text L5 points are stable locations where natural dust clouds accumulate. These points are often targeted for scientific observation due to their stable nature. In contrast, the Text L1 and Text L2 points are only pseudo-stable and require station keeping. Gateway's orbit must be constantly monitored to maintain its position around Text L-2. The Text L2 point's distance from Earth simplifies radio communication with the station. Since the Moon rarely blocks the line of sight, ground stations can communicate almost continuously. This near-continuous communication is a major advantage over a low lunar orbit. The Text NRHO orbit also passes through Earth's magnetotail, a region of complex space plasma. The station can conduct unique research on solar wind interaction and radiation shielding in this area. This new research will be critical for protecting astronauts on the journey to Mars. The Text NRHO orbit, therefore, is not just about fuel, but about science and safety as well. On the diagram, we see the full coverage map of the Moon available from the Gateway. The station's altitude allows it to see nearly the entire side of the Moon facing it at any time. This wide view is useful for mapping and for choosing future landing sites for Artemis. The Text NRHO path is maintained using the Text PPE module's powerful solar electric thrusters. This system applies small, continuous force rather than large, short burns like chemical rockets. This continuous, gentle thrust is what makes the Text NRHO orbit so fuel-efficient. Now watch as a simulated crew transfer from Orion to the human landing system. The entire process is complex, but Gateway makes the final leg of the journey much simpler. The station is a flexible solution for logistics, adapting to future mission requirements. As the Artemis program progresses, Gateway will grow and evolve into a true deep space port. The structure will act as a gravitational slingshot point for spacecraft moving onward to Mars. This means the station saves even more fuel for Mars-bound missions leaving its orbit. The Montext to NRHO orbit truly represents the next generation of orbital mechanics applications. The principles of the three-body problem are now being leveraged for sustained human presence. The Gateway is not just a destination, it is the vital hub connecting Earth to the solar system. This is the permanent outpost that will enable humanity's next great leap into deep space. The legacy of Gateway will be the infrastructure that enables the first footprints on Mars. The efficiency of the Context NRHO made this entire long-term vision possible. Now a final epic view of the Gateway, ready for the next Artemis crew and the future. Subscribe to see more complex space physics explained with clarity and cinematic vision.